So what we want to look at now is hypothesis testing, right? Okay, so let's consider this example over here. This example is a somewhat informal example, because how I will work it out is we're not going to use, to work it out, we won't use the actual mechanics of hypothesis testing, right? Where you would have your test statistic and so on, right? These first couple informal examples, we will work out in a more sort of common sense way, right? And then the point about this is to give you an idea of, well, to give you an introduction for hypothesis testing. Okay. All right. So what we have is we have this question here, right? Uh, we know that it's given that boys of age of 9 years, right? They have a mean weight of 85 pounds, right? Okay, so there's a children's home, right? And there's a complaint against this children's home that your boys in this home are underfed, right? Okay, so what is done is you take 25 of these boys, right? Of age 9 years, right? So what we're looking at is boys of age 9 years, right? And we measure the weight, right? And you take the average for the 25, right? And that average is small x bar, right? Which is 50, right? And what we want to, well, question ask us, well, what can be concluded about the complaint, right? Okay, so is the complaint valid, right? Uh, the boys on average of that are 9 years old have an average weight of 85, right? Uh, these boys at the children's home, right? When you measure them, right, and you get the average weight, right? The average weight is 50, right? Okay, so you see that the 50 is significantly, very significantly less than the 85 pounds, right? So there is validity in the complaint that that the boys are underfed, right? Okay, so that's really just looking at it logically, right? But let's introduce the notation that we would use in hypothesis testing, right? Okay, so when you're doing hypothesis testing, right, you have gonna have two hypotheses, right? A null hypothesis, which is H0, and an alternative hypothesis, which is H1, right? Okay, so the H1, right, represents the question to be answered or the theory that you want to test, right? Okay, so what's the theory that you want to test in this problem here, right? What you're looking at is you're looking at actually at boys of age 9 years, right, in this children's home, right? And you want to test the hypothesis that the mean weight of those boys in the children's home, that mean weight is less than 85, right? Okay, and if there's evidence to support this hypothesis that the mean weight mu is less than 85, then you can conclude that the boys are being underfed, right? So the hypothesis that we want to test over here is that the mu, right, and this mu over here, how you want to read this mu is the the mean weight for your population, and the population in this case would be 9-year-old boys in the children's home, right? Okay, so H1 is mu is less than 85, right? Okay, so this is the theory, the question that we want to examine, right? The mu is less than 85. And when you're doing the hypothesis testing, as I said, you're going to have a null hypothesis and an alternative hypothesis, right? Okay, so sometimes it's actually easier to really just state the alternative hypothesis first of all, right? And then once you have your alternative hypothesis, to state the null hypothesis, it's usually fairly easy to get it from here, right? What you do is you take this inequality here and you just use an equal sign instead, right? So one thing you want to note is that your null hypothesis is usually stated with an equal sign. Okay, so for this setup with a null hypothesis and an alternative hypothesis, right? What you're gonna do is, what you're looking for is gonna decide, well, you decide in around this H0 over here, right? So the two things that you're gonna decide is whether you're going to reject this H0, right? So by rejecting is, it means that the evidence is stating that this claim H0 is false, right? Okay, so either you reject H0 or you do not reject H0, right? So that's just a phrase and it's used in stats. There's probably good reasons for it, right? Okay, so you either reject the H0 or you do not reject the H0, right? And the do not reject, you could roughly think of it as you accepting H0, right? But the phrasing that we want to use is we either reject the H0 or we do not reject the H0, right? Okay, so in this case, do we reject the H0 or not, right? So this H0 is saying that your mean weight of the boys, 9-year-old boys in the home is 85, right? This is what the H0 is saying. But the evidence that you got, right, that when you take the 25 boys and you measure them and you take their average weight, right, you get that the average weight is small x bar, which is 50, right? And so evidence is not supporting this hypothesis over here that the mu is equal to 85, right? Okay, so in this case, what you're going to do is you're going to reject this H0 in favor of H1 over here, right? So given that the evidence is that this small x bar is 50, right? What we're going to do is we're going to reject H0 in favor of H1, right? Now, this over here, this is, I am not using any statistics or anything over here. What I'm just doing is just reasoning this over here based on the values that I have, right? Right, so given that the average weight of the 25 boys is 50, right? And that 50 is significantly less than 85 over here. What we're doing here is we're going to reject this H0, right? So reject the H0 in favor of the H1, right? Okay, so in this case, your evidence here supports the claim that the boys are underfed, right? So it supports the claim that H1 is true, right? And that the mean weight of the boys is less than 85, and so the boys are being underfed, right? Let's take a look at a very similar problem. What I did is I just changed the sample mean weight over here, right? So it's the same setup, right? I have we investigating children's home, right? The boys in the children's home, and specifically the boys of age 9, right? You want to determine if the boys are being underfed, right? So the average weight of boys of 9 years old is supposed to be 85 pounds, right? And what you do is you find 25 boys in the children's home, right, of age 9 years, right? You take the average weight, and in this case, the average weight is 84.99, right? Okay, so what we want to do is we want to investigate if the complaint has any validity, right? So again, what we want to do is we want to set up the hypotheses, right? So what are the hypotheses, right? You're going to have an H0 and you're going to have an H1, right? So H1 is, as I said, the question that we want to answer or theory that we want to investigate and so, right? Okay, so what's the question that we want to answer, right? The question that we're looking at is whether the mean weight of the boys is in fact less than the standard value, which is supposed to be 85, right? So your H1 over here is the mu less than 85, so same as the example that we just looked at, right? And once you have your H1 over here, you form your H0, right? Okay, so now what you do is for the values given in this second problem over here, we're going to decide if we're going to reject H0 or we're not going to reject H0, right? Okay, right. So in this case, the average weight, when we take the 25 boys, we measure them, find the average weight, what we get is 84.99, right? Right, so what you can say over here is that the average weight that you find, right, isn't significantly different from the 85, right? It's just slightly, very slightly less than the 85 over here. So really, you can't reject this fact over here, right? You don't have enough evidence over here to reject H0, right? Because it seems as if H0 is in fact true, right? That the boys in the children home, right? That the actual mean weight over here is in fact 85, right? Okay, so this is, remember, this is a hypothesis, right? And the hypothesis is stating that for the boys in the children's home, that the mean weight is 85, right? You do an experiment over here. You measure 25 boys, you take the average weight, and you get 84.99, right? And 84.99 is really, in fact, supporting that, well, the actual population mean over here for the boys of age 9 is, in fact, 85, right? So what you can't do over here is you can't reject the 80 over here, right? So in this situation here, you cannot reject 80, right? And well, there is no evidence to support. If you can't reject H0, right? Well, then there's no evidence to support H1, right? And if there's no evidence to support H1, well, according the complaint that you're looking at, that the boys are underfed, right? Which is represented by this H1 over here, that complaint doesn't have validity, right? It's not true, right? Because the evidence is supporting that the mu is actually equal to 85, right? So in this situation over here, in terms of hypothesis testing, what we say is that we cannot reject 80, right? So informally, you're saying that 80 is true, but you don't really want to state it like that. How you state it is that you cannot reject 80. Okay, so let's look at a third example of this. It's the same setup, right? Uh, Only this time when we measure the 25 boys, right? The average weight that we get is 84.8, right? Okay, so again, what you're doing is you're saying that the standard weight of boys of 9 years is 85 pounds, right? And you're checking to see if the boys in the children home, right, if their weight is in fact less than 85, right? So you're checking to see if they're underfed, right? Okay, so the hypothesis again would be your null hypothesis, which is the theory that you're testing, right? You're testing to see if the mean weight of the boys is less than 85, right? So this is the question that you want answered, right? So this is the H1 over here. And then you get the H0 from this by using an equality sign over here, right? Okay, so given this evidence over here, right, do we reject H0 or do we not reject H0, right? Okay, so what we have over here is 84.8, right? Now it seems as if we're getting a little bit of evidence that the the weight of the boys is less than 85, right? But what you want to realize is that it's not significantly less than 85, right? Okay, and because it's not significantly less, right? Now, as I said, this is an informal example, and we need to eventually, well, formalize how we're going to actually decide to accept, not reject H0 or to reject H0, right? But at this point in time, what we're doing is we're trying to understand the reasoning behind the hypothesis testing, right? Okay, so in this case over here, I get 84.8, and what I'm saying here is that, well, at least without any sort of further evidence, right, this 84.8 really isn't that much different from the 85, so you really don't have sufficient evidence over here to reject 80, right? Okay, so in this case, again, what you're gonna do is you cannot reject H0, right? Okay, so what that means is if you can't reject H0, right, you don't have evidence to support this H1 over here, right? So again, what you're gonna say here is that you don't really have evidence that the H1 is true, right? Or you don't have evidence that the boys have been underfed, right? All right, okay, so let's look at this one here, right? It's the same problem again. In this case, when you find the average weight, right? The average weight is 80.94, right? Okay, so your null hypothesis, as before, was mu is equal to 85, and the alternative hypothesis is mu less than 85, right? So the same setup as the previous three problems, right? The only difference here is now the average weight that you find is 80.94, right? Now, given this 80.94, right, you're going to decide, well, am I going to reject the 80, or is it that I can't reject this 80, right? Now, I have 80.94 over here, and you're seeing that that's actually less than the 85, right? If you compare it to the previous problem, right, in the previous problem, I had 84.8, right? And that was fairly close to the 85, and because of that, I couldn't reject the 80 over here, right? But in this case here, right, I have, I observe 80.94, right? Now, that actually is giving me evidence that I can actually probably reject this 80, right? But it really, I mean, it isn't really that far, right? So what's the difference between the 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 mu over here, which is 85, and the 80.94, right? So the difference over here is 4.06, right? So basically you have a difference of 4 from the weight that you actually measure, right? This average weight over here is the difference between this 80.94 and the 85 is 4, right? So there is some difference, and the question that you want to ask yourself is, well, is that difference, is that a significant difference, right? And if it's a significant difference, then what we're going to do is, well, if it's a significant difference, right, then what you'll have to do is you have to reject the H0 in favor of the H1, right? So that's the key thing over here in the hypothesis testing, right? Once you decide on your hypotheses, right, you're gonna have a certain test statistic over here, value of a test statistic, right? Observed test statistic, right? So you're gonna have some value over here, and this value, using this value, you're gonna decide whether you're going to reject H0 or you're not going to reject H0, right? And you're rejecting H0, you're not rejecting H0 based on if what you have over here, if it's statistically significant, right? And so you see in the 80.94 and you see in the 85 over here, and the question is whether the difference over there, right, which is about 4, right, whether that is statistically significant, right? Over here, basically I hand waved, right, and I said, well, in this case the difference was just 0.2, right, and that was not significant here, right? But I'm saying over here in this case, right, because the difference is 4, I just can't push it under the carpet and say that this is if it's significant or not, right? I need to investigate it further, right? Okay, so how do I investigate it further? All right, so what we do is let's consider a couple of things over here, right? So we got 80.94, right? When we measured the 25 boys and we took the average, right? And what we're doing is we're comparing that against the 85, right? Okay, so the question we want to ask ourselves is, well, is this 80.94, right? It's less than 85. The difference is about 4, right? Is that difference from the 85, is that due to, say, like a minor variation, right? Is that due to, say, like a fluctuation or so, right? Okay, so more formally, if you now over here, when you have H0 here, and you're working with this, right? What you're doing is you're assuming that the mu is equal to 85 over here, right? So if we assume that the mu is equal to 85, and is it possible to get 80.94 by chance, right? And if it's possible to get this 80.94 by chance, right, then you wouldn't be able to reject the H0, right? So, and by getting it by chance, I'm saying is not getting this 80.94 is not statistically significant, right? Okay, so that's one possibility that we want to consider, and then the second possibility, well, is that the boys are actually underfed, right? But really, to work out this question, what would we really consider in here is this first possibility. We need to investigate this over here, right? Okay, so what you need to do is you need to decide if the difference between your observed value, which is the 80.94, and your hypothesized value, which is the 85, right? If you want to determine if that difference was due to random fluctuation or not, right? Okay, so what's the difference first of all, right? The difference, the observed value is 80.94, and your the hypothesized value for the population mean is 85, right? Okay, so your difference over here is 80.94 minus 85, which is minus 4.06, right? Okay, so you want to determine if this minus 4.06, if that's a significant difference or not, right? Now, how do you determine if it's a significant difference, right? Well, what you're doing is you actually want to see if the difference, if it's probably due to like a random fluctuation or not, right? Okay, and well, what's a random fluctuation, right? How you measure a random fluctuation in a population, right, is by using the standard deviation, right? Okay, so what you do is you take this over here, right, the actual difference that you got, right, and you compare it against the standard deviation, right? Now, the standard deviation in this case is given by sigma and root 10. So sigma is the standard deviation for the population, right? And then when you consider sample mean, right, this would be a standard deviation over here, right? So we talked about that, right? If a random variable for your population is represented by x and has standard deviation sigma, then when you form the x bar, the sample mean, right, then the standard deviation is in fact smaller and is given by sigma and root 10, right? Okay, so the standard deviation that we're going to be comparing against is the sigma and root 10, right? Because what we're working with over here is observed sample mean, right? So what we're going to be comparing this minus 4.06 against, right, is the standard deviation for the x bar, which is sigma and root 10, right? And these would be values given to you in your question, right? And this value over here for this particular question, right, is 2.32. It's not stated over here, right, in this particular problem, but we'll eventually get a question, right, where it's the same rubric over here, but where the standard deviation would be stated, right? But for the time being, this is the standard deviation that we're working with, right? And this is the difference that we got, right? Now, the difference that we got, right, when we measured this 80.94, the difference from the 85 is minus 4.06, right? And what we do now is we compare that against the standard deviation, which is 2.32, right? Okay, and how you compare is, well, you compare the magnitudes, right? So you take the minus 4.06, right? And you divide it by the standard deviation, right? And you get this value over here, right? Now what you're looking for is, well, you're looking for the size of this here, right? Okay, and in particular, you're looking to see, well, for example, if the size is bigger than 1 and so on, right? And in this case, what we get is we get that the minus 4.06 under 2.32 is minus 1.75, right? Alright, so how can we decide, well, I mean, it's minus 1.75, and as I said, it's bigger than 1, right? So it seems as if it's going to be significant over, well, sorry, it's not bigger than 1, the magnitude of it is bigger than 1, right? Okay, so it seems as if it's going to be significant, right? But how can we actually decide, right? Okay, and you'd see when we do the hypothesis testing that we're gonna have a definite way of deciding whether it's significant or not, right? This over here, as I said, this is an informal explanation, right? Now, how we're gonna actually do the problem when you're doing hypothesis testing wouldn't be precisely like this, right? You're gonna actually form this quantity over here, right? But you won't quite do it this way, right? Okay, so this is really just to give you an idea of what's going on, right? So far we have this minus 1.75. Now it turns out that this quantity over here, right, what this is this is an observed value of a test statistic, right? Now this sort of object over here, if I have big X bar over here, right, so random variable big X bar, this in fact follows a standard normal distribution, right? Okay, so this follows a standard normal distribution, which I have sketched over here, right? Okay, and the minus 1.75, right, is a z value in your standard normal, right? And the minus 1.75, I have it indicated over here with this blue arrow, right? So the minus 1.75 is located over there, right? Okay, so what you want to notice is this minus 1.75 is actually far from the zero over here in terms of a standard normal, right? Now, how I can formalize that a little more, right, is this over here is this minus z 0.05, right? This is a z critical value, right? Z critical value equal to minus 1.645, right? And what that means is that the probability of the random variable z taken of a value less than this minus 1.645, right? So in other words, the probability that the random variable z takes a value on this red interval over here, right? That probability is equal to zero point zero 0.05, right? So you have a small probability basically of ending up in this critical region over here, right? And you see this minus 1.75 actually is in this critical region over here, right? So the probability of it, this minus 1.75 actually, this over here ending up in this red region just by chance alone is actually small, right? It's less than zero point zero 0.05, right? So this over here, this minus 1.75, chances of this occurring, in other words, the chances of getting the 80.94, right? The chances of getting this over here by chance alone, right, in fact, is less than zero point zero 0.05, right? Okay, so the chances of getting this 80.94, right, is really, you consider the probability of you ending up in get having a value inside this red interval over here, right? And the probability of ending up inside this red interval over here by chance alone, right, is zero point zero 0.05, right? Okay, so this over here to actually get this 80.94, it didn't happen by chance alone, right? So what that means is that your assumption over here that the mu is equal to 85, right? That that is not a correct assumption, right? Because if it is a correct assumption, right, if the mu is actually equal to 85, the probability that you would have gotten the 80.94 is just too small, right? So what that means is this assumption was wrong in the first place, right? Okay, so because this over here is, according to the statistics and so, is the 80.94 is far from the 85, right? It's so far from the 85 that right. So this 80.94 is so far from this 85, right? It means that most likely it didn't occur by chance alone, right? And for it to not occur by chance alone, right, means that this 85 over here was wrong in the first place, right? Okay, so um, a similar way to look at this is we could consider, right, we have the mean of 85 over here, right? The the x bar, right, the sample mean would actually have mean 85 over here and it would have a certain standard deviation, right? Now, when we get this 80.94, right, right, if we assume that the mean mu is equal to 85 over here, right, and if when we actually do the experiment we get 80.94, right, notice the probability of you ending up over here, right, in this red interval over here, given that the mean is actually 85, right? The probability here is small, right? The probability here is 0.05, right? So if you actually end up over here, right, in this, and we get 80.94 over here, right? If you actually end up here, right, it means that this 85 over here, right, this assumption was wrong in the first place, right? So most likely this mu zero over here is not at 85. The actual population mean is probably somewhere like over here, right? A little closer, right? Right, you're using and this is not, as I said, this is not the way we're going to actually do it. This is basically to give you an idea of how you're using the probability distribution of the x bar, right, to decide whether to accept the h0 or not, right? And we'll probably talk a little bit more about this, right? But as it is, the 80.94, right, is giving you evidence that the mu0 is equal to 85 is not true, right? So the 80.94, this over here, right, being significantly less than the 85, right, the evidence says that you have to reject h0 in this case, right? And if you reject h0 in this case, right, that means that you have evidence to support h1. And if you're going to support h1 over here, it means that the complaint is valid and that the boys are being underfed. Alright, so let's consider the same problem, but now we're going to use the information that the standard deviation is given to us, right? And we're also given a level of significance, right? So we need to understand what these things mean, right? So it's the same problem, right? You have, you know that boys of age 9 years, they have a standard mean weight of 85, right? You're looking at this children's home to check to see if the boys that are 9 years old, that they're being underfed, right? Okay, and what you do is you take 25 of them, you measure the weight, take the average of that, right? And what you get over here is an observed value for your sample mean, which is 80.94, right? Now, you're given that the population, right, the population of the weights of boys 9 years old, right, that the standard deviation is 11.6, right? Okay, so based on this, right, what you want to do is you want to determine if the complaint that the boys are being underfed, if it has validity at a significance level of alpha is equal to 0.05, right? Okay, so and then we're assuming here that the boys in the home are normally distributed, right? The weights of the boys at the home, it's normally distributed, right? Okay, so you want to work out this problem, right? Okay, so now doing these hypothesis testing problems is actually not much work at all, right? Once you understand what you're doing, right? The calculation is actually pretty fast, right? And this answer is a long answer. Right, and matter of fact, this first answer over here is again really just to sort of explain the theory a little more, right? The second answer that I have here, right, where I use a test statistic, right, would be the way that you'd actually want to do it, right, and it'll work out faster, right? It's probably not entirely clear as to how this test statistic works, right? So that's why I'm going to do it this first way, right? It's called answer one in the notes, to give you an idea, because it's a little clearer over here what your rejection region is, right? Okay, so we answering the problem, right? Now, as I explained before, what you're going to have is you're going to have a null hypothesis and you're going to have alternative hypothesis, right? And the null hypothesis and the alternative hypothesis is the same, right? The question that you're investigating is that the boys are being underfed, so that the mean weight is less than 85, right? Okay, and once you have your alternative hypothesis over here, right, what you need is a null hypothesis, and the null hypothesis you can basically get by taking this over here and using an equal sign, right? So you have your null is mu is equal to 85, right? Alright, okay, so if you're testing hypotheses like this, right, where your alternative hypothesis is an inequality of this sort of form, right, then this sort of test, the test that we're going to use over here is a one-sided test, also called like a one-tail test, right? Why it's called one-tail is eventually we're going to be looking at a probability distribution, and we're going to have a rejection region over here that's consistent of one tail here, right, on this side, right? As compared to if you have a two-sided test, right? A two-sided test is when, let me show you an example of a two-sided test. Okay, so in this situation over here, for these hypotheses, right, because this now is not it's not a inequality like this. Right. This case over here is a two-sided inequality, and if you want, this is a one-sided inequality, right? This is mu less than 85, and this is mu not equal to 8 over here, right? And in this sort of situation over here, right, this test over here would be two-sided because when you look at your rejection regions over here, it'd be formed from two tails, right, on the side, right? Okay, as compared to what we have in this case over here, where it's just one tail over here, right? Okay, so if you have your alternative hypothesis where it's say your mu is less than or if it's greater than, then what you're going to be working with is when you test your hypotheses over here, what you're doing is you're using a one-sided test. All right. Okay. So this is the problem, right? Your hypothesis, your null hypothesis, is the mu is equal to 85, right? Now, the evidence that you get, right, when you measure the 25 boys and you get the average weight, right, you get 80.94, right? Okay, and you want to determine if this 80.94, if this is statistically different from this 85 over here, right? Now, in order to do that, if you're going to use statistics, right, to determine if this 80.94 is statistically less than the 85, right? What you would need is some probability distribution, right? You need to work with some probability distribution. And, well, the probability distribution that you're going to be working with is the probability distribution for the average, right? Okay, so this is an observed sample mean, right? You want to recall that this is an observed value of the random variable big X bar, right? And the random variable big X bar in this situation over here is going to be normally distributed, right? Because you're told that the weights of the boys are normally distributed, right? Okay, so if the weights of the boys, if you have a random variable representing the weight of a single boy, right? And then you form your sample mean, right? That sample mean, if the individual random variables are normally distributed, then the sample mean is also going to be normally distributed when the sample mean is going to be normally distributed when your standard deviation is known over here, right? So when you have a known standard deviation and you working with a normal population, right? Then the big X bar is normally distributed with mean mu 0 and standard deviation sigma squared on it, right? And this sigma is the given population standard deviation, which is 11.6, and the n over here is the sample size, which is 25, right? Okay, so what's the mu 0 over here, right? Well, you see in this problem, what you're doing is you're testing this hypothesis, right? 80 is equal to mu is equal to 85, and you're testing the alternative, right? So you're deciding which one of these are true, right? Now, the point about having this 80 is equal to mu is equal to 85, right, is, in fact, remember what you're doing is you deciding whether you want to reject or not reject this 80 over here, right? So essentially, you're working for the problem is hinging around using this 80 here, right? So in your problem, you're going to be using that the mu is equal to 85, right? So this X bar over here, you're going to assume that it has a mean of 85, and what you want to do is you're using your evidence in the problem. In particular, you're using the value of the small X bar to decide if this is a good assumption, right? But that's the assumption that we're starting with, and so we use that in our calculations over here, right? Okay, so far we have that your big X bar over here is normally distributed with mean 85 over here, and it has a standard deviation of sigma on root 10, right? Okay, which is 11.6 on 5, right? Root of 25 is 5, right? So this 11.6 on 5 is your standard deviation for the X bar, right? Okay, so Right. So X bar normally distributed with mean 85 and standard deviation 11.615, right? And we worked that out previously. That was 11.6 on. Right, 11.6 on the 5 was 2.32, right? Anyway, so this 11.6 on 5 is 2.32, right? And we have the probability distribution for the X bar, right? Okay, so the mean is 85, and what we got is we got an observed sample mean of 80.94, right? And what I said earlier is this 80.94, right? It is too far from the 85, right? So the probability of getting this 80.94 over here by chance alone, right, is small, right? It's too small, and what that implies is that this assumption over here that the mean was actually your population mean is 85, right? This assumption is false, right? Okay, but what we want is we want a standard way of deciding, right? Now, the standard way of deciding is based on the significance level that's given to us, right? So we're given a significance level over here of zero point zero 0.05, right? Okay, so that significant level over here is in fact going to determine what's called a rejection region, right? Okay, so what's your rejection region, right? Your rejection region over here is values less than 81.18, right? Okay, so you're seeing over here that you can in fact work out, right? The fact that X bar is normally distributed with a known mean and known standard deviation, right? Means that given this zero point zero 0.05, right? So this is given to you, right? Okay, so you want to recall that we had this sort of problem over here, right? If we had a random variable x over here, right? We had, say, a probability. So let's use part B over here, right? So I have a random variable x over here, and I have a probability given to me, right? What I needed to do is, what this sort of problem did is you needed to figure out the value of the small x here, right? So that the probability that the big X is less than the small x is equal to 0.05, right? So if you want this as sort of using doing a normal calculation for probabilities, but doing it in reverse, right? You're given the probability and you want to figure out what the value of the small x is, right? And that's what we do over here, right? Okay, so we know X bar, we know its normal distribution, we know its mean, we know its standard deviation. And what we're given over here is 0.05, right? Okay, so you're given 0.05 over here, and once you're given this 0.05, what you could do is you could work backwards and figure out this 81.18, right? Okay, so what this is saying is the X bar over here, the probability of it being less than 81.18, that is 0.05, right? Okay, so what you're doing is you're using this 0.05, your level of significance that was given to you, right? You use that to figure out, so this is the alpha over here, the alpha is 0.05. You use that to figure out the 81.18, right? Okay, and what we're looking at is values of the big X bar less than 81.18, right? And the probability that the X bar is going to take a value that's less than this 81.18. That probability is 0.05, right? Okay, so this over here, that your values are less than the 81.18, that would actually be your rejection region, right? Okay, so this is the same diagram, but it's sketched a little better over here, right? So it's I have the 81.18, which is this 81.18. And this red interval over here, this is your rejection region, right? All right, okay, so we use the alpha is equal to 0.05. We use the given information to figure out a rejection region, right? Now, the idea here is that if you assume that the population mean is in fact is 85, right, and you do an experiment and you get a value over here such as this 80.94, right, that lies in this rejection region, right, then the probability of that occurring for mu 0 is equal to 85, that's a low probability, right? Probability would be less than 0.05, right? Okay, so what that implies is that if you have this assumption that the mu 0 is equal to 85, you do your experiment and you get a value over here that's so far from the mu 0 is equal to 85. What that means is that this assumption over here is wrong in the first place, right? So that's why you call in this a rejection region, right? A rejection region over here would be a region that is far from your assumed population mean, right? And if you actually do your experiment and you get a value in the rejection region, that's indicating to you that this assumption over here, that the mu 0 is equal to 85, is actually false. Right, okay, and the next way to look at this rejection region is you're looking at this statement over here and the probability that your big X bar being less than 81.18 is 0.05, right? Okay, so what this is saying is, as I have stated in the notes, right, is that if the 80 is true, right, if that were true, right, then you would have 0.05 probability of getting a value in this rejection region over here, right? Okay, so and how you can look at it that way, or you can look at it this way, that if you actually do get a value, right, in this rejection region, right, then that is indicating that your assumption or that the mu over here is actually equal to 85. That was wrong as an initial assumption, right? Okay, and if it's wrong as an initial assumption, right, what that means is if this assumption over here is wrong, it means that you're going to reject H0, and therefore you reject H0 in favor of H1, right? Okay, so what it's saying here is that we're rejecting H0 in this case. So for your problem, when you observe a sample mean of 80.94, right? This 80.94 is giving you evidence to reject this H0 in favor of H1. And so that the boys are actually, there's evidence that the boys are actually being underfed. Alright, so let's see a second way to do this problem, and this is the more standard way of doing the problem, right? So let's just recall what I just did previously, right? Okay, so what I did previously, I had my hypotheses, my null hypothesis, which is mu is equal to 85, and I had my alternative, which was mu less than 85, right? And what I did is I formed a rejection region, right? And the rejection region, right, I got by using the probability distribution of the X bar, right? And using the level of significance that was given to me, right? Okay, so the rejection region that I got was this rejection region here, which is the X bar is less than 81.18, right? And the observed value of my test statistic, which is 80.94, right, in fact actually lies in the rejection region, right? And if it lies in the rejection region, well, then what that means is you reject the H0, right? And hopefully you understand the explanations for it, right? That the fact that it's lying in this rejection region over here means that your assumption over here that the mu 0 is equal to 85 is not plausible, because the probability of you ending out so far over here from the mean, right, is just too low, right? Okay, but a fast way to look at this is you form your rejection region, right? And if your test statistic, which is the 80.94, right, if it lies in the rejection region, then you reject your H0 over here, right? Okay, so this is how we worked out the problem without scaling, right? With using the X bar directly, right? Okay, so to recap very quickly, you have your H0, you have your H1, right? So previous answer, what we formed was we formed a rejection region, which was X bar is less than 81.18, and we had an observed value of 80.84, right? And this 80.94, right? And this 80.94, it lies in your rejection region, and because it lies in your rejection region, well, if it lies in a rejection region, then you reject your null hypothesis in favor of your alternative hypothesis. Okay, so right, in the answer before, right, what we were doing is we were working with the big X bar, right? But how you actually work out these problems is you just scale everything, right? Okay, so instead of working with the big X bar, right, what you do is you scale the big X bar to standard normal, right? And you do that in your normal way, right? Remember the big X bar has mean, mu, and standard deviation sigma on root n, right? So this object, big X bar minus mu on sigma on root n, this is going to have a standard normal distribution, right? Okay, so in this case, the mu that we're looking at is coming from the mu equal to 85 from your assumption over here from your null hypothesis, right? And then the standard deviation and the sample size is given to you, right? Okay, so you form your standard normal, which is z, and now what we want to do is we want to see what happens when we work with z, right? Now, with the x bar, your rejection region was values less than 81.18, right? Okay, so when you scale, right, what's going to happen is that this rejection region over here is going to scale also, right? And what it will scale to, so this entire picture over here, right, which is in terms of the x bar, will scale to standard normal, right? So it'll scale like this over here, right? Okay, so what you're going to see is the rejection region, which was x bar less than 81.18. That's now going to scale to the big Z being less than minus Z.05, right? In other words, this critical Z less than this critical value over here, right? Okay, well, what do you need to decide in your problem, right? What you need is a rejection region and a test statistic, right? Okay, so what's the rejection region in the case when you scale it, right? When you scale it, the rejection region is that the big Z is less than minus Z.05, right? And the test statistic over here is also going to scale, right? When you scale this test statistic of 80.94, right? What you're going to get is you're going to get minus 1.75, right? Okay, so the picture for the x bar is going to scale for the z, and also your rejection region is going to scale, and your test statistic is going to scale, right? Now remember over here what we did is the test statistic was the actual observed average weight, which was 80.94, and we said that that lies in the rejection region. It's less than 81.18, so it lies in the rejection region, and therefore we're going to reject the H0 over here. The mu 0 is equal to 85, right? Now similarly, once you scale everything, right, the rejection region will scale, right? So now you have a scale rejection region in terms of Z. The test statistic is going to scale, but the actual reasoning or the methodology to determine whether you're going to reject or not reject, it's the same, right? What you do is you look at the test statistic over here, and you check to see if it is in the rejection region or not, right? And if this test statistic is actually in your rejection region, right, then what you're going to do is you're going to reject the H0 in favor of the H1, right? And well, how do you scale, right? How you scale everything is you just really using the fact that the x bar is normally distributed with mean 85 and the standard deviation, and this is how you're going to scale, right? And in particular, how you scale your test statistic over here is this: you put in this 80.94 into this expression over here, so you're going to get the 80.94 minus the 85 on the denominator here, and that would actually work out, so you've seen it over here, that works out to be the minus 1.75, right? Okay, now when you're actually doing your problems, right, when you're doing your hypothesis testing problems, this is what you'd use over here, right? You'd use scaling, right? You won't work with the x bar directly. Usually you won't work with the x bar directly. What you'll work with is you'll work with the x bar when it's scaled to standard normal. And over there, what you do is you'd use your test, in this case here, what you do is you use a test statistic and you'd use a scale rejection region. Alright, so let's take a look at the formula that, or the results that we're going to use in the hypothesis testing, right? So what I did is I gave you an explanation and hopefully you get an idea of how this methodology works, right? But really, as I said, you could do it fairly quickly, right? Just using these results, right? Okay, so what I have is I have a random sample, right, of size n from a normal population with known variance sigma squared, right? Okay, and I'm looking at population means, right? So my null hypothesis of the form population mean mu is equal to mu zero, and you want to read this mu zero is equal to a constant, right? Okay, now once I have my null hypothesis here, and I know that my population is a normal population with known variance, right? Then the rejection regions, right? So an example of a rejection region is this is an example of a rejection region. This red shaded interval over here is an example of a rejection region. Your rejection region would depend on what your alternative hypothesis is, right? So in this case, for this problem that we just looked at, right? Remember your alternative hypothesis was inequality where it was less than over here, right? Okay, so if you have an alternative hypothesis of this form, mu less than a value mu zero, right? Then your critical region or your rejection region would take the form z less than equal to minus z alpha, right? So it's going to take this form over here, z less than equal to minus z alpha, and you want to notice that what you have is a minus z alpha over here, right? The alpha in for this particular problem was 0.05, and here this is you stated generally, right? Okay, so this over here is helpful because really it's just giving you criteria for working out your problem, right? You have your null hypothesis on, and then based on the form of your alternative hypothesis, you get the form of your rejection region or your critical region. Okay, and then what you do is you use this test statistic, right? You work out this value, right? In this case, the value was minus 1.75, right? So you're using this formula over here to work out a value, and then finally what you do is you check to see if that value is in your rejection region or not, right? And in this case, the value is in the rejection region. Okay, so let's see an example of using this, but in the case of a two-sided test. All right, so let's consider this problem, right? A manufacturer is claims that a fishing line has a mean breaking strength of 8 kilograms, right? You want to test the hypothesis that mu is equal to 8 against the alternative hypothesis that mu is not equal to 8, right? Okay, so you're using a random sample of size n is equal to 50, right? And you in fact given that the mean break-in strength, so what you're given is a small x bar, is 7.8, right? Okay, so what we want to do is we want to test the hypothesis h0, which is mu is equal to 8, right, against the alternative hypothesis h1, which is mu is not equal to 8, right? So you want to notice that this is two-sided over here, right? You're given the observed sample mean, which is the 7.8. So the small x bar is equal to 7.8, right? Okay, so we're working it out using this result here, right? Okay, so first thing I do in this answer is I work out what the test statistic is, right? Okay, so your test statistic you work out using this formula that the big Z is equal to the big X bar minus mu on sigma under root 10, right? Okay, so we need to figure out what the test statistic is, right? So the observed test statistic, when you're using observed values, you use the common letters here, right? Okay, so the observed test statistic, small z over here, right, is small x bar minus mu on sigma root 10. Small x bar is given to me 7.8. The mu is what I assumed in the H0, which is 8 over here, right? The standard deviation was given to me 0.5, and the sample size is 50, right? So what I have is square root of n over here, which is square root of 50, right? Okay, so I work this out over here, and this gives me my test statistic, right? This is minus 2.83, right? All right, so if you're working out these hypothesis testing problems, you need two things. You need the test statistic, right? And you need your critical region or your rejection region, right? And this over here is telling you the form of your critical region, right? The form of your critical region would be it's two-sided, right? So it's of this two-sided over here, right? So you're gonna have critical region consisting of two intervals, right? One on the right tail and one on the left tail over there, right? Okay, so it's the union of two intervals. That is what this notation means, right? This over here, this z bigger than or equal to z alpha on 2 is this red interval over here. And this z less than or equal to minus z alpha on 2 is this left interval over here, right? Right. To determine what these intervals are, you need your critical values, which would be the z alpha on 2, right? And then, so you need the z alpha on 2. Matter of fact, that's what you need, because on this side over here, what you have is minus z alpha on 2, right? Okay, so I need the z alpha on 2, right? And remember what the alpha is. The alpha is coming from a level of significance that was given to you in the problem, right? So the level of significance given to us was alpha is equal to 0.01, right? Okay, so what that means is that the alpha on 2 is 0.005, right? Okay, so what I need is the value of z over here, right? So I need the z critical value, so I need the small z 0.05, and the probability that the big Z being bigger than this value, right? The probability of that occurring is 0.005. Alright, okay, so I need my my Z critical values, and remember I can in fact get my Z critical values from the T distribution table, right? These values inside here are all T critical values, right, for your different degrees of freedom. But if you're down here, right, with the infinity over here, infinite number of degrees of freedom for a T distribution means that what you're looking at is you're looking at a standard normal over here, right? So down here, what you have is this last row over here, Z critical values, and what you want is a Z critical value for 0.005, right? So the Z critical value for 0.05 is 2.576, right? Okay, what I have in the notes over here is 2.575, so I probably got this from a different table, right? But it's essentially the same thing, right? So let's proceed with calculation here, right? Okay, so these are my Z critical values, and matter of fact, it won't make a difference because of the test statistic that I'm going to use here, right? All right, so couple things that I needed to work out the problem would be, first of all, your test statistic, right, which we worked out already, which is the minus 2.83. And then we also need the critical region in this case, which would be two-sided, right? Okay, and the critical region is, according to your formula over here, is Z bigger than Z alpha on 2, which is this interval here together with the interval, the corresponding interval on the left hand side, which is Z less than or equal to minus Z alpha on 2, right? Okay, so that is your critical region, or also known as the rejection region, and we worked out that the Z 0.005 from the table was 2.575, right? Okay, so we have this over here is 2.575, and this over here is, well, it's the minus Z critical value, so I have minus 2.575, right? And now, so now I know what my rejection region is, right? Because I know what these Z values are now, right? This is 2.575 on this side, and this is minus 2.575 on this side, right? And the last thing you want to do is you want to see if your test statistic, which is the minus 2.83, right, lies in your rejection region over here, right? And you want to notice what I have is minus 2.83, and that's actually less than minus 2.575, right? So therefore, my test statistic lies in the rejection region, right? And because it lies in the rejection region, what you need to do is you need to reject H0 in favor of H1, right? Okay, so the mean, the evidence doesn't support that the mean break-in strength is 8 kilograms, right? It supports that, well, it's actually not equal to the 8, right? Alright, so if you're doing hypothesis testing where you have a null hypothesis H0 and an alternative hypothesis H1, right? There's two types of errors that could be made, right? You can make a type 1 error, right? And what a type 1 error is that you actually you reject H0 when in fact it is true, right? We'd be interested in is we would be interested in calculating probability of type 1 errors, right? Alright, so your probability of type 1 committing a type 1 error, right, is called size of the test or level of significance, and you denote your probability as alpha, right? Okay, on the other hand, what you have is you have a type 2 error, right? And a type 2 error is when you do not reject H0 when the H0 is actually false, right? Now, the probability of committing a type 2 error is denoted by beta, right? And in order to calculate the probability of committing the type 2 error, you need a specific alternative hypothesis, right? Now, this HA over here, alternative hypothesis, is not the same as H1, right? This is an actual equality over here, right? So we will see an example of this. Alright, so let's see some examples of calculating the probability of type 1 and type 2 errors, right? Okay, so this example here, the hardness of a certain metal, right, is known to be normally distributed with a standard deviation of sigma is equal to 10, right? Engineer is performing this hypothesis test where your null is mu is equal to 170 and the alternative hypothesis is mu is bigger than 170, right? And your sample size is n is equal to 25, right? Okay, so part A over here, right, they give you a rejection region, right? They give you that rejection region is that the big X bar is bigger than 172, right? Okay, so given your null hypothesis over here, right, and given your rejection region, right, which is the big X bar is bigger than 172, what we need to do is to ask you the question is to figure out what's the probability of committing a type 1 error. Okay, so recall that probability of committing a type 1 error, right, is the probability of rejecting H0, right, when it's actually true, right? Okay, so in this case, when do you reject H0, right? Well, you reject H0 when the X bar is bigger than 172, right? So what we need to do is we need to work with the big X bar over here, right? Okay, so we're going to be rejecting when the big X bar is bigger than or equal to 172, right? Okay, so it's the probability of rejecting H0 when it's actually true, right? So that is what your type 1 error is, right? H0 is actually true, right? So H0 in this case is mu is equal to 170, right? So we're using this mu is equal to 170 because it's, well, it's true, right? And your rejection region is phrased in terms of the big X bar over here, right? Okay, so we need to, in order to calculate our probabilities, we would need the probability, we need the distribution of the x bar. Right? Okay, and what's the distribution of the x bar? Well, it's normally distributed, right? Your population is normally distributed, which would mean that the x bar is normally distributed. The mean of that normal distribution is the 170, which is coming from the H0, which is true, right? And then the standard deviation for the x bar is sigma squared. The variance for the x bar is sigma squared on n, right? Okay, so the sigma is 10 and the n is 25, right? So we get the variance is 125 over 4, right? Okay, the critical region is given in part A over here, right? It says that the engineer decides to reject H0 if the sample mean x bar is bigger than 172, right? So the critical region is the bigger than 172 over here, right? Okay, so what we want is the probability of the type 1 error, probability of getting a type 1 error, right? Okay, so that's the probability of rejecting H0, right? When H0 is actually true, right? Okay, now when would you reject the H0, right? Well, you reject H0 when your observed sample mean lies in the rejection region, right? So a type 1 error occurs when you get an observed sample mean that lies in the rejection region, right? So your probability of a type 1 error is a probability, as I have over here, that the observed sample mean lies in your rejection region, which is the big X bar bigger than 172, right? And the probability that your observed X bar lies in a big X bar bigger than 172 is really just the probability that the big X bar is bigger than 172, right? Okay, so to work out the probability of the type 1 error, we just need the probability that the big X bar is bigger than 172. And this isn't hard, right? Because the X bar is normally distributed, right? So you do this in your standard way. What you do is you scale, all right? So you're going to scale the X bar to Z, right? And then when you scale over here, right, this 172, you also need to scale, right? So you scale by subtracting the mean and dividing by the standard deviation of the x bar, right? Okay, so we scale in over here, and when we scale, you're going to scale this 172, right? So what you're going to have is 172 minus mu divided by standard deviation, which is this over here. So this is your standard way of calculating the probabilities for a normal distribution. What you do is you scale to standard normal. Okay, and then what you have is the probability of the big Z being bigger than 1. And then from your table, what you get is that that probability is 0.1587, right? So the probability of your type 1 error is 0.1587. Okay, so for the same problem, let's now consider calculating the probability of a type 2 error, right? So let's recall what a type 2 error is. A type 2 error occurs when you do not reject H0 when H0 is actually false, right? Okay, and in order to calculate probability of a type 2 error, you need a specific alternative hypothesis, right? Okay, so in this case, the specific alternative hypothesis, right? So the H0 over here is that the mu is equal to 170, right? But the specific alternative hypothesis over here is given to you in the problem, which is mu is equal to 173, right? So you're going to be using that in your problem, right? And given that your specific alternative hypothesis is 173, what we want to get is you want to get the probability of a type 2 error, right? Okay, so a probability of a type 2 error is that you do not reject H0, a probability of not rejecting H0, given that the H0 is false, right? And the H0 being false, you actually need to use a specific alternative value. 0 being false, in this case, the H0 mu is equal to 170, right? As I said, you need to use a specific alternative value for the mu, right? And that's given by 173, right? Okay, so probability of your type 2 error is probability that you not rejecting the H0, right? Now, what's the probability of not rejecting H0, right? You reject H0 when the big X bar is bigger than 172, right? So probability of not rejecting H0 is you're not going to reject H0 when the big X bar is in fact less than equal to 172, which is what I have over here, right? So what I want to do is I want to work out this probability here, right? Okay, but I need the distribution of the big X bar over here, right? Now, what's the distribution of the big X bar? The big X bar is normally distributed, right? With mean mu and variance sigma squared on n, right? But the mean mu is actually given to us now, right? The mean mu is equal to 173, right? Okay, so using your alternative hypothesis, which is the mu is equal to 173, we feed that in over here to the probability distribution of the big X bar, right? So we have this probability distribution of the big X bar. And now once we have this, we can use this in our calculations, right? Okay, so we want the probability of not rejecting H0 and probability of not rejecting H0. If you want, is the inverse of the rejection region or the complement of the rejection region. And the complement of the rejection region is the big X bar is less than 172. So we want probability that the big X bar is now less than 172, and we just need to work out this probability here, right? Okay, and working out this probability, you just do what you normally do when your random variable X bar over here is normally distributed. What you need to do is scale, and in particular, you need to scale this 172, right? And you do that by having 172 minus the mean divided by the standard deviation, right? And in this case, the mean is 173, which is this 173 given to you over here, right? Okay, so you work this out and you get probability that the big Z is less than minus 0.5, and then using symmetry on your table, you get that this probability, your type 2 error is 0.3085, right? Okay, and here we have a diagram indicating this over here, right? The X bar, right, is normally distributed with mean 173 over here, right? What you looking for is probability that the big X bar is less than 172, right? So for this condition over here, what you'd be doing is you'd be accepting H0, right? So we need to calculate that probability, right? Probability that the big X bar is less than 172, right? Okay, and in the notes here, right, the big X bar bigger than 172 is a rejection region, right? And if you take the complement of that, right, what you're looking at is the big X bar less than or equal to 172. So that's an acceptance region, right? Okay, so this over here, if you less than or equal to 172, this is the acceptance region, right? And the probability of getting type 2 error is the probability that the X bar takes values less than or equal to 172, right? And the required probability is the shaded area over here, which we worked out in the problem, which was 0.3085.